All right. Um, so you should have gotten your. No, I'm sorry, not. Yeah, I'll grade your homework assignments as soon as I can. Hopefully, I can get that done for you today. Um, and then I'll send them to you. But the solutions are posted, so check those out when you get a chance. All right. So we were talking about equivalence relations. Okay, and let's review the definition of equivalence relation. Um, a relation, tilde, on a set A, is an equivalence relation when it satisfies the following three properties. For every x in A, x is related to x. That's reflexivity. Symmetry for every x in y. X is related to y, implies y is related to x. Transitivity for every x, y, and z. X related to y related to z, and y related to z implies x is related to z. And we looked at this equivalence relation on the integers. So this equivalence relation, this symbol here, usually just call it equivalence, on the integers given by x is equivalent to y when x plus y is even. So we showed that that's an equivalence relation. And we showed it using a certain notion of evenness. Right? The notion of evenness that we used was x in the integers is even when x over 2 is still an integer. Right? So that's one way to characterize evenness. And then we give a proof. So for next time, so last time I said for next time, do the following. Let's do the proof again using a different notion of even. I mean, they're equivalent, of course, but a different way of thinking about evenness, a different characterization of evenness, if you will. An integer x is even when there is another integer k such that x is 2k. So let's look at an alternative proof for that. What am I doing here? So exercise assigned last time. Right. So x and z is even when there is k and z such that x is 2k. So now define x related to y in z when x plus y is even. Okay. So show this is an equivalence relation. So reflexive. Okay, remember the definition of reflexivity. So, by the way, again, we have definitions, and one has to know the definitions. That's step one. Okay, so in order to show that something is an equivalence relation, one needs to know the definition of equivalence relation, right? Obviously. So that's step one. So again, you got to know those definitions. Um, and again, that's like a sticking point for students because throughout grade school and calculus and things of that sort, things are never presented to you as definitions. Or if they are presented to you as definitions, I mean, they're introduced over years and years of time. I mean, you start learning the definition of a rectangle from kindergarten, right? And then you just talk about it more and more and more. So these ideas are just sort of like ingrained in your mind at this point. But now, this is the way things are done. Here's a definition. Boom, let's learn it. Okay, now let's do some proofs about it. So, I mean, rather than, doing something over 12 years, we do it over, 12 minutes. So reflexivity, for every x is related to x. Okay, so given x in z, okay, how would we show that x is related to x? Well, you need that x plus x, which is equal to 2x, is even. Was that even? So a number is even when it's equal to 2k for some k. So is that even?
Yeah, that's even.
Of course. Yeah. Which is even. So x is related to x. Symmetry. Again, the first two are pretty simple. Given x and y in the integers, assume x is related to y. Okay, so we want to show that x related to y implies y is related to x. Right? So, what does it mean so we assume, it's an implication statement, we assume x is related to y. So, therefore what? X plus
y is even.
Yeah, which means what? X plus y is equal to
1 plus x.
Well, what does it mean to be even, first of all?
There's some k that's an integer such that x equals 2k.
Yeah, so
2k plus y?
No, x plus y is even. Didn't say x was even. Said x plus y is even.
Oh, just set it equal to 2k then?
Yeah, is equal to 2k. X.
Okay, that makes more sense.
I didn't say x was even, right? I mean, like 3 plus 5, that's even. Although x is not. All right, so x plus y is equal to 2k for some k and z. Right, not k in the rational numbers, k and z. Right. Well, now, right, for some k, which implies that, y plus x, which is equal to x plus y, is equal to 2k. Therefore, y is related to x. And then the last one was transitivity. Given x, y, and z, right? And what was transitivity? Transitivity is if x is related to y and y is related to z, then x is related to z. Okay, so given x, y, and z, we need to do what? It's an implication statement. So we need to do what?
Assume x is related to y and y is related to z, and then prove that x was related to z.
Right. So assume x is related to y and y is related to z. By the way, that I've been noticing this a little bit more here and there in the homework assignments. The temptation now is to just say, like, because X is related to Z, and then start talking about stuff. Right? So it kind of, that's the temptation. So it kind of goes like this. Right? So you're trying to show P implies Q. Right? So you assume P is true, and then you want to say, then you want to prove that Q is true, right? So that's the direct proof. Assume P is true, and then show that Q is true, and uh, this is the direct proof. We assume P is true, and you want to show Q is true. So then folks are tempted to do this because Q is true. Right, da, 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 keep talking, blah, 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 and then you're done. End of proof. That's the temptation. Right? What's wrong with that? What's wrong with saying something like that?
Because it's assuming Q is true.
Yeah, exactly.
And you're trying to prove that Q is true.
Precisely. What you are trying to prove is that Q is true. So you can't say at any point Q is true until you've proven it. Right? But once you've proven it, that's the end of the proof. So that's the last thing you're going to say, that Q is true. At no other point can you say Q is true. I mean, when we say it like this, it's kind of like, well, yeah, of course. Okay, but that's the temptation when you're learning how to write proofs. Right? Because you have some kind of goal in mind, so you want to say something about that goal. So the temptation is just to say it's true. I don't know. I mean, I'm not exactly sure why that is the temptation, but people do it. So just just watch for that. All right, because sorry, I'm doing it. So assume that this x is related to y and y is related to z. Therefore, what? What does that mean? X is related to y and y is related to z.
X plus y is even and y plus z is even.
Mm-hmm. Are both even. All right, which implies that x plus y equals
2K.
2k, and y plus z
2K.
same k.
No.
Right? I mean, like 3 plus 5 is 2 times 4. 7 plus 2, or 7 plus 3 is 2 times 5. Right? So it can't be the same k. We need a different
L.
Yeah, 2l. For some k and l in z. Now, what can I do with those? Can I do with these two equations? Let's see what we should do.
System of equations.
Well, no, not really, unfortunately. Well,
Setting them equal to each other.
oh, well, they're not equal, right? Because K and L are different. They could be the same, but probably not. Just add them together. So x plus y plus z is equal to, adding these equations. All right, x plus y plus z is equal to
2L plus 2K.
yeah, 2k plus 2l. Alright, so x plus 2y plus z is 2k plus 2l. So, what can I do now? Notice I'm stacking my equations here. I'm actually solving something here. Let's move the 2y over here.
Ooh, which is even.
Which is even, right? Because it's 2 times this. Or minus.
Yeah, we have to. Yeah,
which means that x plus z is even, so x is related to z. And that's it. So that's transitivity. All right. So if you didn't do this before today, okay, go over these. You got to go over these examples on your own to, to solidify this material in your mind. So, what we're going to do another example. I mean, look at that example because we're going to do another one like it. I'll assign to you for next time. But please, guys, when I say for next time, do this. Give it a shot before you come to class. It's not to hand in; it's just for discussion. But the discussion doesn't mean a lot if you haven't tried it. So I do my part, you do your part, right? That's how we learn. I assign you this for next time. So find 10 minutes at some point to do it, or at least give it a go. Right. So we were on this one. Did we finish it? Right. So here's another example. Given a set a part. So please remember this definition and think about this definition. We're going to talk about partitions again. A partition of A. Partitions are important. Is a collection of non-empty subsets of A that are disjoint, and the union is all of A. So you're cutting up A into different parts. It's called a partition. And these subsets A1 to AN, they're called the blocks of the partition. Okay, so for example, here's the numbers 1 through 9. Here's a partition of 1 through 9 into 4 blocks. So the blocks are non-empty, they're disjoint, and the union is the whole set. All right, just what the word means, really. So now, given a partition, let's define an equivalence relation. So you've got some fixed partition. We're going to define an equivalence relation on the, on the set A, for that partition. So a relation tilde on A, define a relation tilde on A by x is equivalent to y when x and y are in the same block. And that's an equivalence relation. So let's do the proof. The proof is let x be an A. Certainly x is in the same block as itself. So x is related to x. Let x and y be an A. Assume that x is related to y. All right, that is, x is in the same block of the partition as y. Therefore, y is in the same block of the partition as x. So y is related to x. It's got that symmetry. Transitivity. Let x, y, and z be an A. Assume that x is related to y and y is related to z. Therefore, x and y are in the same block, and y and z are in the same block. And because blocks are disjoint, both pairs are in that unique block, which does contain y. Right? X and y are in the same block, and then y and z are in the same block. Which block is it, though? It's not two different blocks. It's the block that has y in it, because both pairs contain y. Therefore, x and z are in the same block. So x is related to z. All right, so we did talk about that. Now, the theorem is as follows. Given an equivalence, let's do a definition before the theorem. Given an equivalence relation twiddle on set A. So we've got an equivalence relation on A. So for each x in A, so square bracket x, okay, new notation, equal to the set of all y in A such that x is related to y. So this set is called an equivalence class, or the equivalence class of x. Okay, and the theorem is as follows. If tilde is an equivalence relation on A, then the equivalence classes partition A. So an equivalence relation gives you a partition, and a partition is an equivalence relation. So the equivalence relation gives you the partition. That partition are these equivalence classes. So what do we have to show? So we need to show that the equivalence classes are disjoint and their union is all of A. All right, so let x and y be two equivalence classes. Bracket x and bracket y be two equivalence classes. Okay, so consider two arbitrarily chosen x and y in A. Well, this is going to be awkward. let x and y be an A. All right, so they're arbitrarily chosen elements of A. Just any elements of A. And let's consider their equivalence classes. Bracket x and bracket y. Okay, what do we want to be true? What do we want to be true?
That they're disjoint.
That they're disjoint, or right. So I mean, what are the possibilities? I mean, you would like that they're disjoint, but they're not disjoint. Then you want them to be what? The same. Either they're disjoint or they're the same set of elements. There's no overlap, essentially. If they overlap, then they're the same. Okay, we want to show that either x intersect y is empty, or that they're equal. Right? Either they're empty, the intersection, or they're exactly the same. How can we do that? So assume, how do you prove an or statement? Remember, ors are just like implications via the implication tautology. So assume that the intersection is non-empty, right? If you're trying to show that A or B is true, well, the implication tautology is that this is equivalent to A naught implies B, right? Right? The or is equivalent to that. Let me write this down. So remember, A or B is logically equivalent to A naught or B. Implies B. A naught implies B. So let's prove that. So assume that bracket x intersect bracket y is not empty. Right? Then you want to show that they're actually the same. So assume bracket x intersect bracket y is non-empty. And let's prove that bracket x equals bracket y by showing that bracket x is a subset of bracket y and bracket y is a subset of bracket x. Okay, the proofs are actually identical, just switching around the roles of x and y, so you only have to show that. So actually we only have to show that x is a subset of y because the proof for y subset of x is the same, just switching around the roles of X and Y. All right, so we just need to show that bracket X is a subset of bracket Y. So let Z be an element, Z be an element of bracket X. Okay, we haven't used the assumption about the intersection yet. Let's use this assumption now. We haven't used that yet. Okay, because bracket X intersect bracket Y is the empty set, what's there? There is what? Oops, what did I do? I messed something up. Because the intersection of those two sets is non-empty, what's got to be there? Hello, guys. Because the intersection of X and Y is non-empty, what's got to be there? What must exist?
Z.
Z is an element of the equivalence class for X. It's not necessarily in the overlap of X and Y.
They must be equal.
Not yet. Because the intersection is non-empty, there's got to be an element there. Have we encountered that element yet? The answer is no. We haven't encountered that element yet. Okay, the two sets. So here's bracket X. Here's bracket Y. And their intersection is non-empty. Now, we've got this Z in bracket X. Right, but Z doesn't have to be inside here. So what's here?
Something.
Something. What do you want to call it? Can't call it Z's is what I'm getting at. So you got to call it something. What shall we call it? There's A, N, or W, going at the end of the alphabet, in bracket X intersection bracket Y. That is, right, W is in bracket X, and W is in bracket Y. So by definition, this means that, well, what was the definition of bracket X? It's the set of all Y such that X is related to Y. Right? So this means that X is related to W, because W is in the equivalence class, and Y is related to W, right? Because W is in the equivalence class for Y. Now we need to show that bracket x, or sorry, that z, which was in bracket x, is also in bracket y. That's what we were getting at. So we haven't looked at z yet. Okay. Also, so let me just finish this up. Because z is in bracket x, right? We get that x is related to z. Now, to show that z is in bracket y, right, to show that z is in bracket y, we need that z is related to y, or y is related to z. We've got that z is in, x is related to z. Now we need to know that y is related to z. Okay, well, y is related to w. Okay, so by symmetry, so x is related to w. By symmetry, w is related to x because it's an equivalence relation. So we have that x is related to z. Right, we have that y is related to w, and w is related to x, and x is related to z. So what? Right, y is related to w, w is related to x, and x is related to z. By using transitivity,
Y is related to Z.
yeah, transitivity twice, y is related to z. Right, as required. Y is related to z, so z is in the equivalence class of y, and we're done. All right. So this two equivalence classes are the same. We showed that bracket x is a subset of bracket y. We don't have to show that bracket y is a subset of bracket x because it's the same proof, just exchanging the roles of x and y. Okay, it's the proof has a symmetry to it in that sense. Okay, so two equivalence classes, they're either disjoint or they're the same. Right? So we have that are disjoint. Okay, and their union of the equivalence classes must be all of A, right? Because right, each element of A is in its own equivalence class, right? By reflexivity. Right? And so we're done. So the equivalence classes, they partition. So you're not going to be held responsible for that proof of that, although it might be a nice exercise for you to go over that. But that's just the main fact about these equivalence relations is that equivalence relations, the equivalence classes, give you this partition of A. And given a partition of A, that gives you an equivalence relation. So they're one and the same thing. Now, it's not always like crazy obvious what that partitioning is, but we can find it. So, for example, right? Remember, our relation this on Z, where x is related to y when x plus y is even. All right, the equivalence classes are the equivalence class of 0, which includes what? So 0 plus what is even. Right? When is 0 plus x even? 0 plus x is equal to x. So when is 0 plus x even?
When x is even?
Yeah. Set of all x such that x is even. Right, but that's actually the same as the equivalence class of 2, the same as the equivalence class of negative 16, same as the equivalence class of 20, so on and so forth. So, whichever element that you pick in the integers that is even, it is in the equivalence class for 0. But, of course, 1 is not in the set of all x such that x is even. But what is the equivalence class for 1? Set of all x such that what? X is what? Right, so when is x plus 1 is even? X plus 1 is even when x is
When x is odd.
when x is odd. Right, and that's the same as the equivalence class of 3, the equivalence class of minus 15, so on and so forth. So, by the way, this theorem implies that the theorem above implies that if x is in, or sorry, if y is in the equivalence class of x, then the equivalence class of y is the equivalence class of x because of symmetry. Because if y is in x, then the equivalence class for x, then the overlap of the equivalence classes of x and y includes x. Yeah, includes x and y. Okay. Well, actually, do that. Do that one as an exercise. It could stand a proof. Doesn't really need it, but think about that for next time. So for next time, so let this be an equivalence relation. Okay, use the theorem above. To prove that y, an element of the equivalence class of x, implies that the equivalence class of x is equal to the equivalence class of y. Remember that, two equivalence classes are either the same or disjoint. So all you have to do is show that, these two equivalence classes are not disjoint. There's something in there. Essentially, the intersection has x and y both. You don't have to have that x and y both. Just can show that x is in the intersection of these two equivalence classes, and then you're good to go. Or just y, whichever one you like. So whenever you have equivalence classes, once you see that that's a partition, okay, you're done. So we know we're done here because, right? The integers, they're partitioned into evens and odds, right? An integer is either even or it's not even, but not even means it's odd, right? So once we look at the equivalence class of 0, right, that's the set of all even guys. The equivalence class of 1, that's the set of all odd guys. But that's the entire set of integers, so we're done. Well, what about all the other numbers? What about their equivalence classes? Well, if you take anything that's already in the equivalence class of 0, like 16, its equivalence class has to be the same. Right? 16 is an element of the equivalence class of 0. Therefore, 16 and negative 16, for that matter, the equivalence class of 16 and negative 16 is the same as the equivalence class for 0. So often there's like a preferred representative for the equivalence class, right? I mean, why would you choose negative 16 as a representative for this equivalence class? I mean, 0 is like a more natural choice. 0 and 1. For those computer scientists out there, that's obviously the case because this is the idea of the binary numbers. Although this is not usually the equivalence relation that's used. We don't normally look at x plus y being even. We look at x minus y being even, but it turns out to be the same thing. So here's a generalization of that. So okay, so definition. So given n bigger than or equal to 2, so n and z, with n bigger than or equal to 2, okay, we say that x is equivalent to y. Let's write it. X is equivalent to y modulo n. So this is denoted by x equivalent to y modulo n. So sometimes you put a little n underneath as a subscript of that equivalence, but normally you just forget about it because it's just sort of understood that we're talking about this n, or you can just put it in there or whatever. Okay, so x is equivalent to y modulo n when, sorry I didn't define it, when y minus x is a multiple of n. Equivalently, I shouldn't use that, that is n divides y minus x. So y minus x is a multiple of n, or you can say it the other way around, n divides y minus x. Okay, now when dividing two integers by n, right, you get a quotient and a remainder. That when dividing an integer x by n, we obtain a quotient q and a remainder r, which is an element of 0, 1, 2, a quotient and a remainder r, which is an element of 0, 1, 2, all the way up to n minus 1. Okay, so I'm not sure we're going to have time to do it, but for next time, show that, well, sorry, so in a remainder, that looks like that. It's less than n. It's between 0 and n. Strictly less than n. Therefore, the following sets are a partition of Z. The set of all nk such that k is in Z. So that's everything. That's everything that is divisible by n, all the multiples of n. And then aside from that, multiples of n plus 1. Those are things that have remainder 1. nk plus 2. These are things that have remainder 2 when divided by n. All the way down to nk plus n minus 1. Things that have remainder n minus 1. When divided by n. Right? So if you group integers, if you partition the integers according to their remainder when divisible by n, you get a partition of the set of integers, right? Because that remainder is unique, right? I mean, like 100 divided by 3, right, is quotient, what is it? 33 plus 1/3, right? So quotient 33, remainder 1. Quotient remainder. Right, in other words, 100 is 3 times 33 plus 1. 101 is 3 times 33 plus 2. And 102 is 3 times 33. Right? Or, wait a minute, what did I do? 3 times 33, 34. 3 times 34. 99 is 3 times 33. Right, so we've got this partition. And for next time, show that these are the equivalence classes are the equivalence classes bracket 0, bracket 1, all the way up to bracket n minus 1 for the relation equivalence modulo n. So once you show that, all you need to show is that those are the equivalence classes. You don't need to show that they're disjoint and that they partition Z. We already know that they're disjoint and they partition Z. So once you show that relation gives you this, that relation equivalence modulo n gives you these equivalence classes for each integer, right? Then you know it's an equivalence relation. Right, so this is like, so there's two ways of showing something as an equivalence relation. I mean, showing it gives you a partition of your set, or showing it has those three properties. So here we're just showing it has the, it gives you the partition of your set, in which and we know already that partitions are equivalence relations. Okay, we'll do some more examples next time. Think about that one. That's an important one that gets used a ton. You may have already seen that before. Has anyone seen equivalence modulo n before? Has anyone seen that?
Yeah.
If you're in computer science, like
modular arithmetic.
Modular arithmetic. Yeah, once you have equivalence modulo n, then you get this cool thing called modular arithmetic, and you'll talk a lot about that in modern algebra. Or if you're in computer science, it probably already talked about it. Okay, so that's all for today. We'll see you next